He's a professor of security engineering at Cambridge University. He is the author of the book Security Engineering. He has done a lot of things already. He has been inventing semi-invasive attacks based on inducing photocurrents. He has done API attacks. He has entered a lot of stuff. If you read his bio, it feels like he's involved in almost everything related to security. So please give a huge round and a warm welcome to Ross Anderson and his talk, The Sustainability of Safety, Security and Privacy.
Thanks. Right, it's great to be here. And I'm going to tell a story that starts a few years ago, and it's about the regulation of safety. Just to set the scene, you may recall that in February this year, there was this watch, Enox's SafeKid 1, suddenly got recalled. And why? Well, it turned out that it did unencrypted communications with a back-end server, allowing unauthenticated access. And translated into layman language, that meant that hackers could track and call your kids, change the device ID, and do arbitrary bad things. So this was immediately recalled by the European Union using powers that it had under the Radio Equipment Directive. And this was a bit of a wake-up call for industry, because up until then, people active in the so-called Internet of Things didn't have any idea that, you know, if they produced an unsafe device, then they could suddenly be ordered to take it off the market. Anyway, back in 2015, the European Union's research department asked Aaron Leverett, Richard Clayton, and me to examine what IoT implied for the regulation of safety, because the European institutions regulate all sorts of things, from toys to railway signals and from cars through drugs to aircraft. And if you start having software in everything, does this mean that all these dozens of agencies suddenly start to have software safety experts and software security experts? So what does this mean in institutional terms? We produced a report for them in 2016, which the Commission sat on for a year. A version of the report came out in 2017, and later that year, the full report. And the gist of our report was, once you get software everywhere, safety and security become entangled. And in fact, when you think about it, the two are the same in pretty well all the languages spoken by EU citizens. Sicurezza, seguridad, sûreté, Sicherheit, Trygghet. It's only English that distinguishes between the two. And with Britain leaving the EU, of course, you will have languages in which safety and security become the same. Throughout Brussels and throughout the continent. But anyway, how are we going to update safety regulation in order to cope? This was the problem that Brussels was trying to get its head around. So one of the things that we had been looking at over the past 15, 20 years is the economics of information security, because often big complex systems fail because the incentives are wrong. If Alice guards a system and Bob pays the cost of failure, you can expect trouble. And many of these ideas go across to safety as well. Now, it's already well known that markets do safety in some industries, such as aviation, way better than in others, such as medicine. And cars were dreadful for many years. For the first 80 years of the car industry, people didn't bother with things like seatbelts. And it was only until Ralph Nader's book, Unsafe at Any Speed, led the Americans to set up the National Highways Transportation and Safety Administration, and various court cases brought this forcefully to public attention, that car safety started to become a thing. Now, in the EU, we've got a whole series of broad frameworks and specific directives and detailed rules, and there's over 20 EU agencies plus the UNECE in play here. So how can we navigate this? Well, what we were asked to do was to look at 3 specific verticals and study them in some detail, so that the lessons from them could be then taken to the other verticals in which the EU operates. And cars were one of those. And some of you may remember the Car Shark paper in 2011, where guys from San Diego and the University of Washington figured out how to hack a vehicle and control it remotely. And I used to have a lovely little video of this that the researchers gave me, but my Mac got upgraded to Catalina last week and it doesn't play anymore. So, verschlimmbessern? Man sagt auf Deutsch, oder? Yeah, okay. We'll get it going sooner or later. Anyway, this was largely ignored because one little video didn't make the biscuit. But in 2015, this suddenly came to the attention of the industry because Charlie Miller and Chris Falashek, two guys who had been in the NSA's hacking team, hacked a cheap Cherokee using Chrysler's Uconnect. And this meant that they could go down through all the Chrysler vehicles in America and look at them one by one and ask, where are you? And then when they found a vehicle that was somewhere interesting, they could go in and do things to it. And what they found was that to hack a vehicle, suddenly you just needed the vehicle's IP address. And so they got a journalist into a vehicle, and they got him to slow down and had trucks behind him hooting away, and eventually they ran the vehicle off the road. And when the TV footage of this got out, suddenly people cared. It made the front pages of the press in the USA, and Chrysler had to recall 1.4 million vehicles for a software fix, which meant actually refreshing the firmware of the devices, and it cost them billions and billions of dollars. So all of a sudden, this is something to which people paid attention. Some of you may know this chap here, at least by sight. So this is Martin Winterkorn, who used to run Volkswagen, and when it turned out that he had hacked millions and millions of Volkswagen vehicles by putting in evil software that defeated emissions controls, that's what happened to Volkswagen's stock price. Oh, and he lost his job and got prosecuted. So this is an important point about vehicles, and in fact about many things in the Internet of Things, or Internet of Targets, whatever you want to call it. The threat model isn't just external, it is internal as well. There are bad people all the way up and down the supply chain, even at the OEM. So that's the state of play in cars, and we investigated that and wrote a bit about it. Now, here's medicine. This was the second thing that we looked at. These are some pictures of the scene in the intensive care unit in Swansea Hospital. So after your car gets hacked and you go off the road, this is where you end up. And just as a car has got about 50 computers in it, you're now going to see that there's quite a few computers at your bedside. How many CPUs can you see? You see there's quite a few. About a comparable number to the number of CPUs in your car. Only here the systems integration is done by the nurse, not by the engineers at Volkswagen or Mercedes. And does this cause safety problems? Oh, sure. Here are pictures of the user interface of infusion pumps taken from Swansea's intensive care unit. And as you can see, they're all different. This is a little bit like if you suddenly had to drive a car from the 1930s, an old Lanchester, for example, and then you find that the accelerator is between the brake and the clutch. Right? Honestly, there used to be such cars. You can still find them in antique car fairs. Or a Model T Ford, for example, where the accelerator is actually a lever on the dashboard and one of the pedals is a gear change. And yet you're asking nurses to operate a variety of different pieces of equipment. And look, for example, at the Bodyguard 545. At the one on the top, to increase the dose, right, this is the morphine that is being dripped into your vein once you've had your car crash. To increase the dose, you have to press 2. And to decrease it, you have to press 0. And in the Bodyguard 545 in the bottom right, to increase the dose, you press 5. And to decrease it, you press 0. And this leads to accidents, to fatal accidents, a significant number of them. Okay, so you might say, well, Why not have standards? Well, we have standards. We've got standards which say that liter should always be a capital L so it is not confused with a 1. And then you see that in the bodyguard on the bottom right, milliliters is a capital L in green. Okay, well done, Mr. Bodyguard. The problem is if you look up 2 lines, you see 500 milliliters is in small letters. So there's a standards problem, there's an enforcement problem, and there's externalities, because each of these vendors will say, well, everybody else should standardize on my kit. And there are also various other market failures. So the expert who's been investigating this is my friend Harold Thimbleby, who's a professor of computer science at Swansea. And his research shows that hospital safety usability failures kill about 2,000 people every year in the UK, which is about the same as road accidents. And safety usability, in other words, gets ignored because the incentives are wrong. In Britain, and indeed in the European institutions, people tend to follow the FDA in America, and that is captured by the large medical device makers over there. They only have 2 engineers, they're not allowed to play with pumps, etc., etc., etc. The curious thing here is that as safety and security come together, the safety of medical devices may improve, because as soon as it becomes possible to hack a medical device, then people suddenly take care. So the first of this was when Kevin Fu and researchers at the University of Michigan showed that they could hack the Hospira Symbi confusion pump over Wi-Fi, and this led the FDA to immediately panic and blacklist the pump, recalling it from service. But then, said Kevin, what about the 200 other infusion pumps that are unsafe because of the things on the previous slide? Oh, said the FDA, we couldn't possibly recall all those. Then 2 years ago, there's an even bigger recall. It turned out that 450,000 pacemakers made by St. Jude could similarly be hacked over Wi-Fi, and so the recall was ordered. And this is quite serious, because if you've got a heart pacemaker, right, it's implanted surgically in the muscle next to your shoulder blade, and to remove that and replace it with a new one, which they do every 10 years to change the battery, is a daycare surgery procedure. You have to go in there, get an anesthetic, they have to have a cardiologist ready in case you have a heart attack. It's a big deal, right? It costs maybe £3,000 in the UK. And so £3,000 times 450,000 pacemakers, multiply it by 2 for American healthcare costs, and you're talking real money. So what should Europe do about this? Well, thankfully, the European institutions have been getting off their butts on this, and the medical device directives have been revised. And from next year, medical devices will have to have post-market surveillance, risk management plan, ergonomic design. And here's perhaps the driver. For software engineering, for devices that incorporate software, the software shall be developed in accordance with the state of the art, taking into account the principles of development lifecycle risk management, including information security, verification and validation. So there at least we have a foothold. And it continues, devices shall be designed and manufactured in such a way as to protect, as far as possible, against unauthorized access that could hamper the device from functioning as intended. Now, it's still not perfect. There's various things that the manufacturers can do to wriggle, but it's still a huge improvement. The third thing that we looked at was energy, electricity substations, and electrotechnical equipment in general. There have been 1 or 2 talks at this conference on that. Basically, the problem is that you've got a 40-year life cycle for these devices. Protocols such as Modbus and DNP3 don't support authentication. And the fact that everything has gone to IP networks means that, as with the Chrysler Jeeps, anybody who knows your IP address can read from it, and with an actuator's IP address, you can activate it. So the only practical fix there is to reperimeterize, and the entrepreneurs who noticed this 10 to 15 years ago and set up companies like Belden have now made lots and lots of money. Companies like BP now have thousands of such firewalls which isolate their chemical and other plants from the internet. So one way in which you can deal with this is having one component that connects you to the network and you replace it every 5 years. That's one way of doing, if you like, sustainable security for your oil refinery. But this is a lot harder for cars which have got multiple RF interfaces. A modern car has maybe 10 interfaces. You know, there's the internal phone, there's the short-range radio link for remote key entry, there's there are links to the devices that monitor your tire pressure, there's all sorts of other things. And every single one of these has been exploited at least once. And there are particular difficulties in the auto industry because of the fragmented responsibility in the supply chain between the OEMs and the tier ones and the specialists who produce all the various bits and pieces that get glued together. Anyway, so the broad questions that arise from this include, who will investigate incidents and to whom will they be reported? Right? How do we embed responsible disclosure? How do we bring safety engineers and security engineers together? This is an enormous project because security engineers and safety engineers use different languages. We have different university degree programs. We go to different conferences. And the world of safety is similarly fragmented between the power people, the car people, the naval people, the signal people, and so on and so forth. Some companies are beginning to get this together. The first is Bosch, which put together their safety engineering and security engineering professions. But even once you have done that in organizational terms, how do you teach a security engineer to think safety and vice versa? Then the problem that bothered the European Union, are the regulators all going to need security engineers? Right? I mean, many of these organizations in Brussels don't even have an engineer on staff. Right? They are mostly full of, you know, lawyers and policy people. And then, of course, for this audience, how do you prevent abusive lock-in? You know, in America, if you've got a tractor from John Deere, and then if you don't take it to a John Deere dealer every 6 months or so, it stops working. Right? And if you try and hack it so you can fix it yourself, then John Deere will try to get you prosecuted. We just don't want that kind of stuff coming over the Atlantic into Europe. So we ended up with a number of recommendations. We thought that we would get vendors to self-certify for the CE mark that products could be patched if need be. That turned out to be not viable. We then came up with another idea that things should be secure by default for the update of the Radio Equipment Directive, and that didn't get through the European Parliament either. In fact, it was Mozilla that lobbied against it. Eventually, we got something through which I'll discuss in a minute. We talked about requiring a secure development lifecycle with vulnerability management because we've already got standards for that. We talked about creating a European security engineering agency, so that would be people in Brussels to support policymakers. And the reaction to that a year and a half ago was to arrange for ENISA to be allowed to open an office in Brussels so that they can hopefully build a capability there with some technical people who can support policymakers. We recommended extending the Product Liability Directive to services. There is enormous pushback on that. Companies like Google and Facebook and so on don't like the idea that they should be as liable for mistakes made by Google Maps as, for example, Garmin is liable for mistakes made by the navigators. And then there's the whole business of how do you take the information that European institutions already have on breaches and vulnerabilities and report this not just to ENISA, but to safety regulators and users, because somehow you've got to create a learning system. And this is perhaps one of the big pieces of work to be done. How do you take, I mean, once all cars are sort of semi-intelligent, once everybody's got telemetry, and once there are, you know, gigabytes of data everywhere, then whenever there's a car crash, the data have to go to all sorts of places, to the police, to the insurers, to courts, and then, of course, up to the car makers and regulators and component suppliers and so on. How do you design the system that will cause the right data to get to the right place, which will still respect people's privacy rights and all the various other legal obligations? This is a huge project, and nobody has really started to think yet about how it's going to be done. Right? At present, if you've got a crash in a car like a Tesla, which has got very good telemetry, you basically have to take Tesla to court to get the data, because otherwise they won't hand it over. Right? We need a better regime for this. And that, at present, is a blank slate. It's up to us, I suppose, to figure out how such a system should be designed and built. And it will take many years to do it. Right? If you want a safe system, a system that learns, this is what it's going to involve. But there's one thing that struck us after we'd done this work. After we'd delivered this to the European Commission, and I'd gone to Brussels and given a talk to dozens and dozens of security guys, Richard Clayton and I went to Schloss Dagstuhl for a week-long seminar on some other security topic. And we were just chatting one evening, and we said, well, what did we actually learn from this whole exercise on standardization and certification? Well, it's basically this. That there's two types of secure thing that we currently know how to make. The first is stuff like your phone or your laptop, which is secure because you patch it every month, right? But then you have to throw it away after 3 years because Larry and Sergey don't have enough money to maintain 3 versions of Android. And then we've got things like cars and medical devices where we test them to death before release. And we don't connect them to the internet, and we almost never patch them. Unless Charlie Miller and Chris Falashek get a go at your car, that is. So what's going to happen to support costs now that we're starting to patch cars? And you have to patch cars because they're online. And once something's online, right, anybody in the world can attack it. So if a vulnerability is discovered, it can be scaled. And something that you could previously ignore suddenly becomes something that you have to fix. And if you have to pull all your cars into a garage to patch them, that costs real money. So you need to be able to patch them over the air. So all of a sudden, cars become like computers or phones. So what's this going to mean? So this is the trilemma. If you get a standard safety life cycle, there's no patching. You get safety and sustainability, but you can't go online because you'll get hacked. And if you get the standard security life cycle, you get patching, but that breaks the safety certification, so that's a problem. And if you get patching plus redoing safety certification with current methods, then the cost of maintaining your safety rating can be sky high. So here's the big problem. How do you get safety, security, and sustainability at the same time? Now, this brings us to another thing that a number of people at this Congress are interested in, the right to repair. This is the Centennial Light, right? It's been burning since 1901, right? It's in Livermore in California. It's kind of dim, but you can go there and you can see it. It's still there. In 1924, the 3 firms who dominated the light business, GE, Osram, and Philips, agreed to reduce average bulb lifetimes from 2,500 hours to 1,000 hours. Why? In order to sell more of them. And one of the things that's come along with CPUs and communications and so on, with smart stuff, to use that horrible word, is that firms are now using online mechanisms, software, and cryptographic mechanisms in order to make it hard or even illegal to fix products. And I believe that there's a case against Apple going on in France about this. Now, you might not think it's something that politicians will get upset about, that you have to throw away your phone after 3 years instead of after 5 years. But here's something you really should worry about: vehicle life cycle economics. Because the lifetimes of cars in Europe have about doubled in the last 40 years. And the average age of a car in Britain, which is scrapped, is now almost 15 years. So what's going to happen once you've got, wonderful self-driving software in all the cars? Well, a number of big car companies, including in this country, were taking the view 2 years ago that they wanted people to scrap their cars after 6 years and buy a new one. Hey, it makes business sense, doesn't it? If you're Mr. Mercedes, your business model is if the customer is rich, you sell him a 3-year lease on a new car. And if the customer is not quite so rich, you sell him a 3-year lease on a Mercedes-approved used car, and if somebody drives a 7-year-old Mercedes, that's thought crime. You know, they should emigrate to Africa or something. So this was the view of the vehicle makers. But here's the rub. The embedded CO2 cost of a car often exceeds its lifetime fuel burn. The best estimate for the embedded CO2 cost of an E-Class Merc is 35 tons. So go and work out, you know, how many liters per 100 kilometers and how many kilometers it's going to run in 15 years. And you come to the conclusion that if you get a 6-year lifetime, then maybe you are decreasing the range of the car from 300,000 kilometers to 100,000 kilometers. And so you're approximately doubling the overall CO2 emissions, taking the whole life cycle, not just the scope 1, but the scope 2 and the scope 3, the embedded stuff as well. And then there are other consequences. What about Africa, where most vehicles are imported second-hand? If you go to Nairobi, all the cars are between 10 and 20 years old. Right? They arrive in the docks in Mombasa when they're already 10 years old, and people drive them for 10 years, and then they end up in Uganda or Chad or somewhere like that, and they're repaired for as long as they're repairable. What's going to happen to road transport in Africa if all of a sudden there's a software time bomb that causes cars to self-destruct 10 years after they leave the showroom? And if there isn't, what about safety? I don't know what the rules are here, but in Britain, I have to get my car through a safety examination every year once it's more than 3 years old. And it's entirely foreseeable that within 2 or 3 years, the mechanic will want to check that the software is up to date. So once the software update is no longer available, that's basically saying this car must now be exported or scrapped. I couldn't resist the temptation to put in a cartoon. My engine's making a weird noise. Can you take a look? Sure, just pop the hood. Oh, the hood latch is also broken. OK, just pull up to that big pit and push the car in. We'll go get a new one. Right? This is if we start treating cars the way we treat consumer electronics. So what's a reasonable design lifetime? Well, with cars, the way it's going is maybe 18 years, say 10 years from the sale of the last product in a model range. Domestic appliances, 10 years because of spares obligation, plus store life, say 15. Medical devices, if a pacemaker lives for 10 years, then maybe you need 20 years. Electricity substations, even more. So from the point of view of engineers, the question is, how can you see to it that your software will be patchable for 20 years. So as we put in the abstract, if you are writing software now for a car that will go on sale in 2023, what sort of languages, what sort of tool chain should you use, what sort of crypto should you use, so that you're sure you'll still be able to patch that software in 2043. And that isn't just about the languages and compilers and linkers and so on, that's about the whole ecosystem. So what did the EU do? Well, I'm pleased to say that at the third attempt, the EU managed to get some law through on this. Directive 771 this year on smart goods says that buyers of goods with digital elements are entitled to necessary updates for 2 years or for a longer period of time if this is a reasonable expectation of the customer. This is what they managed to get through the Parliament. And what we expect is that this will mean at least 10 years for cars